Let's see there. Sure. Well, it's 4 o'clock. There's a couple people in Zoom today, probably because of the weather. I really appreciate you guys making it over. I almost sent you a note saying, please drive carefully. Let me start recording on here because we are going to want to have that. Okay, good to see all of you guys. We are smack dab in the middle of the semester, so gotta basically do another stretch. It's just as long as what we've done up until this point to get to kind of the end of everything. Here comes a couple folks. Let me pass out this handout to them and then we'll get started. There you go. Sorry. In terms of announcements, I don't actually have much. There is a homework assignment due Thursday, I think it is. So hopefully you're started on that. I hope it's going okay so far. Definitely let me know if you need any help with it. You can stop by in Zoom or in person. I'll be around after class today. If it starts raining again and you just want to wait until it stops, I'll be doing the same thing. But I'm happy to help out. So feel free to ask me questions about it. I took a look at it. The last few problems from Thursday's homework, probably you might have got, if you got that far, you might have been kind of in this question mark category. I'm not sure how to do it. Well, we're going to go over it right now. So we'll definitely have it all covered. Not a big deal. I started making a recap for last Thursday's class, and I realized it was getting kind of long. So why not, instead of making us all just hurry to write it down, why not just make a nice handout for you? So that's exactly what I did here. I made a nice handout. This is examples of recurrence relations. These are all examples that we did last Thursday in class. So I just decided to kind of put them all together in one place so you can find them real easily. And that's what you've got in front of you right here. So I'll give you this one too. And so what we are talking about are just, well, the ones we did last Thursday, factorial, right? There's a recurrence relation for it. There's an initial condition for it. And then we have the full solution, the explicit formula for it. So that's n factorial. Andrew, here's a, now we're actually getting a good number here now. Here. Then I did the Towers of Hanoi example. So you see that one there. Here's the recurrence relation for it. There's an initial condition. And we actually derived this explicit formula for it by doing iterative substitution. We plugged the equation into itself repeatedly, and we sort of followed a pattern on that and ended up getting the explicit formula out of that. I mentioned the derangements one. Of course, we knew an explicit formula for the derangements a while ago, but then we've also seen some recurrence relations involving derangements as well. And I've got the initial conditions there. By the way, you might notice that the number of initial conditions is a little bit variable here. But we'll talk a little bit more about that as we get into this further. There was the Fibonacci numbers, maybe the most famous one of them all, where the nth Fibonacci number is just the sum of the two previous Fibonacci numbers. And you've got initial conditions for that. And we actually derived the explicit formula for f sub n in class also on last Thursday. So that is good to know. And then the last example that we did on Thursday last week was, this one was a little bit more involved because we had to set up the recurrence relation for the bit strings, right? Bit strings of length n that have two consecutive zeros. So I called those C sub n. That was the notation I used. And we explained this. We kind of went through the explanation of the recurrence relation itself last time. It equals Zn minus 1 plus Zn minus 2 plus 2 to the power of n minus 2. And if we add on a couple of initial conditions, which you can just explore by looking at strings of length 1 and 2, and how many of those have two consecutive zeros, you very quickly get the initial values. But one thing we don't have as of now is an answer for, well, how do we get the explicit formula to how many bit strings of length n would have two consecutive zeros. We have the recurrence relation, but we have not solved the recurrence relation yet. Okay, so these are 5 examples. We went through all of these last time in pretty good detail. Does anybody have any sort of questions about any of these on the side? If you've been looking at them at all, I don't know. Does it make some pretty decent sense? Marcus?
Sorry, with the bit strings, it's like the number of ways you could have 2 zeros, right? Not that you do.
It's actually figuring out all of the ways that you can make bit strings that have 2 consecutive zeros. It will be a comprehensive list. So, we wrote out some cases last time. The bit string either starts with a 1, or it starts with a 0, 1, or it starts with a 0, 0. And that is actually every possible way that a bit string could start. And in each of those cases, we count how many bit strings with 2 consecutive zeros there would be and add them up. It's literally like the addition principle going on here with that. So yeah, it's actually not just could be 2 consecutive zeros. It is this number of strings that do have 2 consecutive zeros. They would have to satisfy that. Yeah, good question. Any other questions so far? I think on Thursday we'll do some group work, and there'll be one with 3 consecutive zeros or 4 consecutive zeros or something like that. You can imagine tweaking the problem a little bit and coming up with some other interesting examples. Or you could say how many bit strings do not have 2 consecutive zeros and try to come up with a recurrence relation for that. So there's lots of ways to kind of tweak this example 5. Or maybe it's not bit strings, maybe it's ternary strings where you have 0s, 1s, and 2s available. And so there'll be different tweaks that you can make on this number 5 that would be very interesting to look at as well. And I think some of them are in the homework, and then I'll be giving you some group work to practice those as well. And hopefully by the time you've done a few examples, it'll feel a little bit more natural to you. Well, speaking of examples, let me give you one more warm-up problem. If you want, you can write this next one down on the bottom of the handout, or you can write it into your notes, whichever place makes the most sense for you. But I'm just going to call this a warm-up, guys. We're going to practice here a problem about climbing a staircase. So here it is. Find a recurrence relation. So we're not going to solve it yet. We're just going to try to write it down. So find a recurrence relation for the number. I'm going to call it S sub n of ways to climb n stairs. Right? If you can climb them 1, 2, or 3 at a time. Reminds me, in our house, my dad would always complain that he had bad knees, but he was always going up and down the staircase, like jumping two or 3 stairs at a time. I'm like, maybe that's why you have a problem. Try taking them 1 at a time. Anyway, so yeah, you've got your staircase here, something like this, right? It's just a little visual of it. And we're talking about climbing n stairs. Okay, so I guess it's actually not that different than thinking about bit strings. You sort of want to think about, well, how does this climb begin? Like, what's the first thing you did? And then once you've taken one move up the staircase, then you really just have a shorter staircase remaining, and you can then apply the recurrence relation into that, right? So you could say that there's sort of 3 ways to start this climb, right? You can start with, let me just see how I have it in my notes here, right? So we have sort of 3 cases. You want to think of it this way? And the first case would be that you start with just a 1-stepper, right? So start with 1 step. So now when you do that, so in other words, you're going to put a little stick figure here, and you're just going to go right to here. just go up one step. When you do that, you're not making any choices anymore. I realize it's a case, it's one of the cases, but as soon as you make it a case, then you don't have any choices. You specified that that's how your first step is going to be. So your choices are going to come from this point onward. And your staircase now has how many stairs left?
N-1.
N-1, exactly. And so the number of ways to finish climbing the staircase would just be what? S(n-1). Right, so in this case, if we do this, there are, we'll just write this down, there are S(n-1) ways to finish the climb in that case. Okay, so you can start with that. Another possibility, you don't have to start with a one step, you could start with a two step. So you could start with taking 2 stairs. And of course, the nice thing is that the cases are not overlapping. You can't start with 1 step and 2 steps at the same, it's one or the other. And in this case, I'm just gonna kind of do ditto symbols if you don't mind, instead of writing it all out again. But we're gonna get S(n-2) ways to finish that climb. And then number 3, I guess I better come over here so I can have enough room to write the rest of it down. But the third case would be start with a 3-step. And in this case, we'll just do the ditto symbols again, and this is S(n-3) ways to finish doing that climb. Okay? And none of these cases can overlap with any other cases, and that's the only cases that there are. Now, I could make this more interesting by saying that he can step up these stairs, or I could also have an option for him to crawl up the stairs. Or to, I don't know, swim up the stairs, well, depending on what the problem is. And in that case, you would have to put some either additional cases, or you'd have to put some coefficients and say, well, there's actually 2 different ways that he could take 2 steps. He could either crawl up them or he could walk up them, right? So you could obviously, again, tweak this example very easily. But anyway, the point being that by the addition principle then, what we know is that Sn is going to be Sn-1 plus Sn-2 plus Sn-3. Just going to be adding them like so. Is there something that's maybe missing though, that we should add to this setup? Yeah.
Initial conditions, you need 3 of them.
Yeah, we're gonna need initial conditions here, and how many initial conditions is kind of, once we see the recurrence relation, it tells us that I'm gonna have to be able to go back 3 previous staircases that are shorter to be able to really use the formula. So we're going to need initial conditions. So usually with the initial conditions, guys, you're literally just going to think about it explicitly. So with a staircase, I don't like to think about staircases with 0 stairs. Just doesn't really make sense. So when you have a physical problem in front of you, it's best to make sure that your n value is something that would make physical sense. So S1, for example, how many ways would there be to climb a staircase that has 1 stair? Just 1, right? You just take the 1 step, there's nothing else you can do. What if my staircase had 2 stairs? 2 ways, what are they, Mason?
1 step, and then another 1 step or 2 steps.
Okay, I can either do the 2-step in 1 move, or I can do 2 single steps. So that's 2 ways to do it in total. What about the staircase with 3 stairs on it? How many ways will there be to do that? 4 ways? Yeah, I think so. 4 ways. You can either take 3 individual single steps, or you can take a double step and then 1 step more, or you can take 1 step and then the double step, or you can take the big jump and do all 3 steps in 1 big go. Right, so you just gotta write them all down that way. So these are your initial conditions. If I gave you this, you could probably figure out S4, S5, S6, and you can now do it using the formula. And I think I mentioned on Thursday last week, if I ask you to tell me, for example, S10, how many ways are there to climb a staircase of 10? Instead of breaking this down, I mean, it's okay to do that. You can break it down. But the problem is it just becomes a mess. I don't know how else to say it. Right, you start breaking it down, you're gonna end up with, you know, a bunch of terms, it's gonna get longer and longer and longer. This is okay, it will work. But it's much easier, instead of breaking it down, it's much easier to build it up. So just figure out, okay, he wants S10, well, let's figure out S4, then S5, then S6, then we'll just use this form, it's much faster. Much easier, right, to do it that way. Okie dokie. All right, any questions here, guys, so far? We've now got a sixth example for your list here, so some good examples. This is a, you know, practice on setting up the recurrence relation. Okay, but as you can see, we also need to learn how to solve the recurrence relations. We did do that on a couple, the Towers of Hanoi and the Fibonacci numbers last time. But today I want to give you sort of a, more of a, I guess, some general rules of solving recurrence relations. So that's kind of what we're going to do next, which is in the next section 7.2. So we're going to be in chapter 7 this whole week, guys. So this will take us a little bit of time. Let me move my little camera here because I'm going to put some notes up on this other board. Hopefully people out in Zoom land are going to be able to see this. Okay. So what I want to talk about is linear. Well, by the way, keep this handout handy because we're going to look at these examples in the context of this new section. Linear homogeneous recurrence relations. That's kind of the title of this little section here. 7.2, linear homogeneous recurrence relations. Well, I need to give you a definition, I guess. That would be a nice place to start. What is a linear homogeneous recurrence relation? So here it is, guys. I have to write it out again. Linear homogeneous. Actually, let's just start with recurrence relation. I'll add linear in a minute. So a linear, sorry, I'll add homogeneous in a minute. So let's just leave off homogeneous for a moment. A linear recurrence relation of order K as the form and if it's okay with you guys, I'm going to use the book's notation. The book decided that they want to use H's for the notation of their recurrence relation. So I'm just going to call it H sub n. And what it's going to look like, guys, is something like this. A1 times Hn minus 1. And then plus A2 times Hn minus 2. And we go dot, dot, dot. The last one is AK times Hn minus K. And then there is potentially an extra term here, which I'm going to write as B sub n. That is added on the right-hand side, where the A sub i's and the B sub j's, right, all of those A's and B's that you see in the equation, those might depend on n. They might depend on n. They don't have to. They could just be constants. That's what I'm saying. They could be constants. So it turns out that, so maybe I'll just add this as a follow-up definition here. So, sorry, there's maybe like 3 definitions in a row really quick to get this all written down. If the B sub n's are all 0, let's just start with that for all n. So if there isn't an extra term at the end here that's added on, then the relation is homogeneous. So a homogeneous recurrence relation would have no last term on the end of it. So that would mean that all of the terms have the previous terms of the sequence, the H's in them, right? And then one more definition, sorry, while I'm getting it all out. If the AI's, so if the A sub i's are all constant, so if A sub I equals a constant for all I, right? So A1, A2, A3, if those are all just numbers, then the relation is called, well, as you would expect, constant coefficient. In that case, it is a constant coefficient relation. Okay, so, your relation may or may not be homogeneous, it may or may not be constant coefficient, but these are basically the form of a linear recurrence relation. So what I think would be helpful now would be to go through our lists. We have now actually 6 examples. We have the 5 on this sheet. And I'd like to just kind of figure out what is the order of each of these? Are they linear or not? Are they homogeneous or not? All that kind of good stuff. And let's just see if we can do that just to practice the definitions. Sound like a good plan? Okay, so let me just start with number 1. So I'm referring to the handout that I passed out at the beginning. So this factorial one, the factorial one is a sub n. I guess I'll write it on the board just so we have a duplicate copy of it here for us to look at. If we look at that one, can somebody tell me on this one what the order would be? What is the k value here? How many previous terms of the sequence does a sub n depend on? Just 1, right? Exactly. So this is order of 1. Okay, so it has order of 1. It is basically, it's linear. It's basically just this part right here, right? It's just this very first part going up to this amount, right? Is it homogeneous?
Yep.
Yeah.
There's no term on the end that does not involve the h's, in this case, the a's. Right, there's no extra term added on the end, so this is homogeneous. And is it constant coefficient? Are the a's, which are the scalars in front of the previous terms, are they all, do they depend on n or are they just constants?
They depend on.
Depends on n, right? This scalar n is not a constant number, it is a function of n, so this is not constant coefficient. See how we're playing this game? So you just go through, you look at the relation, you ask, what's its order? Is it homogeneous or not? Is it constant coefficient or not? And this is just good practice. Let's look at number 2. This is the Towers of Hanoi example. So again, I'll write it on the board just so we can look at it easily. M sub n is 2 times m sub n minus 1, and then with a plus 1 on the end of it, like so. And what would be the order of this one? Anybody want to tell me? Kevin? Yes, go ahead. 1. Yes, exactly. Order is 1. Okay, because we're just depending on the previous term. Is this one homogeneous? I have a number on the end here that doesn't have a term of my sequence involved in it, so this one would be not homogeneous. And what about constant coefficients? Are these all of the scalars in front of all of the terms constant numbers? Yeah. Definitely, yes. So this one is constant coefficient. Excellent. Okay, so that's another example of this idea. Maybe just so I have a little better room, I'm gonna come back over to this space here. Let's just do a couple more of these. I may not have to go through the whole list. We'll see what you guys think. Number 3 is the derangements example. So dn, this is n minus 1 times the quantity of dn minus 1 plus dn minus 2. And somebody want to tell me what the order of this one would be? This time it's 2, right? Because I have to use the 2 previous terms to describe what dn is. By the way, even if dn minus 1 wasn't there, it would still have order 2. It would just mean that the scalar in front of it was 0, which is okay. But the k value would still be based on this term that's furthest back, which would be 2 in this case. Yeah, so it would be order of 2. What about homogeneous? Is this a homogeneous one?
Yes.
I don't see any term, right? I don't see any term on the right-hand side that isn't attached to a derangement value, right? So this is definitely homogeneous. And is this one constant coefficient?
No.
I see this n in front, right? That's not a constant, so it's not constant coefficient. So we're getting some good variety of answers here for just these few examples that we've had up until now. Yeah, maybe. Do you have the idea? Is it enough to get? I mean, there's the Fibonacci numbers. I think the Fibonacci numbers is a pretty easy one. It's just order 2, and it is homogeneous, and it is constant coefficient. And the bit strings one, that's also order 2. That's also constant coefficient, but it has a non-homogeneous term on it. So I think I'm going to be lazy and not write it down. I'll just say on number 4 and number 5, I'll just say, go ahead and practice. See if you can come up with what those values would need to be. Okay. One little remark that I think I'll make, because this is kind of interesting. Did anybody notice on the table the number of initial conditions that you were given? Like on the first one, we were given 1 initial condition. On the second one, we were given 1 initial condition, but then on the derangements example, we were given 2 of them. And on the Fibonacci numbers, 2 of them. Does anybody see a correlation with how many initial conditions I'm giving as compared to anything else, Marcus?
The order has to be the same as the number of initial conditions.
Beautiful. If the order is K, you'll notice I've given you K initial conditions. That's exactly right. Let's write that down in the notes here, guys. For a recurrence relation, this is just a remark. For a recurrence relation of order K, right? In this case, we require K initial values. Some initial conditions or initial values, which could be, I'll just write it as H1, H2, and ... up to HK, although you could start with H0, depending on what kind of a problem it is, you could start with H0, but the point is there's K of them there. Yeah, that seems pretty reasonable. And that's consistent, by the way, with our little staircase example. This was a recurrence relation of order 3, and we had to have 3 initial conditions. So completely compatible with that. Okay, questions so far? What do you guys think? Good, good. Okay, you know what we need to do now, though, is we need to learn how to solve these. It's nice to set them up, and we've done another example, but I'd like to get into the process of solving these, and it's a little bit messy on the notation, I'm not going to lie to you. So we've got to be a little bit careful with that. Okay, so how to solve, and I'm going to start with just how to solve I'm going to assume constant coefficient, also homogeneous. On Thursday, I'll probably talk about non-homogeneous, but for now, I'm going to do constant coefficient, homogeneous, linear recurrence relations. That's the title of this little section, and it's a pretty long title. A lot of adjectives there, all at the same time. I remember when I was learning this stuff, I thought, gosh, that's so restrictive. You know, gosh, I mean, it's got to be constant coefficient. It's got to be homogeneous. So if it's constant coefficient, that one, we can't use it for this. It's not homogeneous. Okay, can't use it for that, right? You get all these, you can't use it for this. Right? This is so explicitly restricted that you might think, well, gosh, what's this good for? Well, it turns out that actually most recurrence relations are like this. I know I've got some examples that aren't, but a lot of recurrence relations are of this flavor. And the Fibonacci example is a great example. It is constant coefficient, homogeneous, and linear. And you might remember how we solved the Fibonacci one last Thursday, because that's going to be basically how we're going to do it in general. So what we do here, guys, is I'm going to kind of label this as sort of a a three-step process. And basically what we're going to do here is we're going to guess. I always love this. Oh, I've got a PhD in math, so I can guess the answer. I'm gonna guess a solution of the form. And it's gonna be h sub n, and I'm gonna denote it as q to the n. So I used the q on Thursday also. It's the same notation. And this is where, I'll put this in a box, kind of the important point here. And this is going to be where q is to be determined. To be determined. Okay, so we're going to figure that out. And essentially what you do when you get to step 2 is you just plug this guess in to your relation everywhere that you see it. So we try this guess, and then we're going to plug this guess into the recurrence relation. Just write out these words here. You just plug it in everywhere, right, to whatever the appropriate powers are, and just try to make that work. And actually, when you do this, you will obtain, so let me just say what you're going to actually obtain when you do that. To obtain the following equation, it's basically going to look like this. You're going to have, what is it going to be? Q to the n on the one side. And then, so I'm going back to this box here, guys. I'm going back to this box. So hn becomes q to the n, and then we'll have a1, this is equal to, right, a1 times q to the n minus 1 plus a2 times q to the n minus 2 and dot, dot, dot up to a sub, what is it, k times q to the n minus k. And notice I'm not going to put down the b term because we are in the homogeneous assumption right now. Again, I'll talk about non-homogeneous equations later. But for right now, it just looks like that. And what you now do, guys, is you cancel as many q's as you can from all of the terms. The fewest number of q's that you have is actually this many over here, the q to the n minus k. If I take this whole equation and in each term I divide through by q to the n minus k, it is going to reduce it to q to the k, right? Equals, and then what will we have here? A1 times, well, this will be q to the k minus 1. And then plus a2 times q to the k minus 2 and dot, dot, dot. And the last term is just ak. Yeah, so that's what it would turn into. So this is actually, I guess I can leave that as the equation. I guess there's maybe just so I have the terminology a little bit more lined up with what is standard here. What we could say is that Q satisfies what is something that is called the characteristic equation. So the Q has to satisfy this equation, which I'm going to write down in a second for you here, guys. By the way, same exact word that we use in the differential equations. When you're solving differential equations, you guess the solution, you plug it into the equation everywhere, and then you get some equation that helps you determine what Q is, right? It's the same thing here. So Q satisfies the following equation: x to the k minus a1 times x to the k minus 1 minus a2 times x to the k minus 2. And we go dot, dot, dot. We keep subtracting. Everything gets subtracted to the left side. So we just make it equal to 0, actually. So this is what you're going to have. And this is the so-called characteristic equation. It's nothing more than just taking this guy right here and just rearranging it. Moving everything to the left side, essentially, is all that's going on. And there are going to be k roots for this equation. Always. They might be repeated. They might be complex numbers, but an equation, I go to these teacher credential program interviews, I'm often on the committee for that, and they'll give people this quadratic equation or something. And they'll say, does this thing factor? Or something like that, or does it have any roots? And people will sometimes say, oh, no, it doesn't. Just because it doesn't look like it factors nicely. My point is, guys, the fundamental theorem of algebra tells us that these equations always factor. They completely factor down into linear factors. It may not be nice factors, but they have to fully factor down, right, into linear terms. So there are going to be k roots here, and step 3 is going to be to find them, okay, including possibly repeat roots or even imaginary roots. So step 3 then is find the roots. Find the roots, and I'm going to call them Q1, comma, Q2, comma, dot, 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 up to Q sub k. There will be k of them. They might repeat. Find the roots of the characteristic equation. Yeah, so you just find those roots, and I sort of lied. I said there's 3 steps. There's actually more like 5 steps, because once we find the roots, we have to do something with them. You might remember, yes, Counselor.
What do you do if the roots aren't real? Are we allowed to work?
You just work with them. Yeah, you just don't flinch. You just put them into your expression, which is what we're going to talk about next.
Okay.
And you just proceed in that manner. It could be that after you have these complex roots, there will be scalars associated with them that could be 0. And that would make those complex numbers go away. We already, even with the Fibonacci numbers, which seems like the nicest sequence in the world, we had roots that weren't that nice. They were real, at least, but they weren't that nice. And, you know, if we were a little bit too nervous, we would have said, oh, well, you know, there's no way this could turn into whole numbers. But then it turns out that that formula for f sub n just involves whole numbers. So yeah, we should just proceed as if nothing's wrong with having complex roots. Okay, let me get my camera fixed here. Step 4, excuse me. Step 4 right here. Well, I actually have sort of a 2 parts to step 4, because it's going to depend on whether any of these roots were repeating or not. So the first part, I'll call it part A, is that if all roots are distinct. Okay, and this just means no repeats, so we don't get the same root more than once. If all roots are distinct, then what we're going to do is we're going to form the following expression for h sub n. So this would, by the way, this would apply to the Fibonacci example. The roots of that Fibonacci equation were distinct roots. You just build linear combinations. So C1 times the first root Q1 to the n, plus C2 times Q2 to the n, and plus dot, 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 plus K, because I only have k roots, times QK to the n. And so there you go. You take your k roots and you build sort of the most general linear expression involving them that you can. Now, something like that would never work if you weren't talking about linear recurrence relations. It's got to be, we're working with relations of a very nice prescribed form, and that's why building linear combinations of these initial guesses is going to be successful. Yeah, see, it won't always work if the relation is not linear. Yeah. So if your recurrence relation was something like this, I'll just give you an example. This is not linear. I can't take the 2 previous terms and multiply them together. It's a recurrence relation, but it's not linear. So if I try to apply this method on this, I'm not going to be able to get the general solution. Okay, so just to be clear, this isn't for everything. It's just for constant coefficient, homogeneous, linear recurrence relations. Everybody doing okay? My 250B class, they were really struggling. I don't know, the weather is getting everybody kind of like in a different state of mind than normal. But I somehow with math always perk up. Doesn't matter. It's like my dopamine rush keeps me in a very happy state of mind. Anyway, so that is if the roots are all the same. And then, of course, it could be that we have repeated roots. I better tell you what to do in that case. This is a little bit more complicated, but you probably remember with differential equations, when you had repeated roots to the auxiliary or the characteristic equation, that you had to sort of tweak the form of your answer. In 250B, what it is you stack x's. A couple of you took 250B with me. Do you remember stacking the x's in front of the terms? Yeah, well, we're going to do something like that here as well, except it's not x's, it's going to be n's. Yeah, it's going to be n's, exactly. So let's write it down. If a root, let me call it q sub I, is repeated, let's say s sub I times, I'm trying to use the book's notation here. So if a root q sub I is repeated s sub I times, then we construct the following expression, guys. I'm going to not call it little h sub n, I'm going to call it capital H sub n with sort of a superscript of I on it. So this is where the notation starts to get kind of annoying. So for whichever root that is, I'm going to build something here. And what it's going to be equal to is a C1 times Q sub I to the n plus C2 times n times Q sub I to the n. So I'm stacking n's instead of x's, right? And we keep going, dot, 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 add this up for a while. And then the last one would be, oh, this is so awful, C sub Si times n to the power of s sub I minus 1 times q sub I to the n. Well, how many terms do we have here? We have s sub I terms, right? You can kind of tell that by the subscripts on the c's. We have C1, then we have C2, then we have C3, up to C sub Si. The powers of n start with the 0th power, and then the first power, and then the second power. This would be the last one that you get. And each of these terms has these qi to the n's on it. Okay, if you want to factor out the q sub I to the n, you can. The book doesn't do that, so I'll just leave it like this. But this is only the part of the solution related to the q sub I. There could be other roots as well. Of course, they could also have repeats. So, and then we have to finally put it all together. And the way we would put it all together, guys, is for the h sub n, which is ultimately what we're looking for, right? We have to do a big summation of all of these individual h sub n super i's. So it would look like that. And we're summing over the values of I. I don't know how many of them I have, so I'm just going to put that index underneath that summation. But whatever the I values could be, there could be several of them. You're just going to add them all up. So you just build this gadget for each of your repeated roots. You build that gadget. By the way, if the root doesn't repeat, you can still use this. You can still use this, and what you'll just end up with is just this first term, which is basically how you made the terms in the non-repeating case. Right? This is really capital H1, this is capital H2, and so on. So it's really what it is. It is compatible with the other notation. Okay, that's step 4. You ready for step 5? I think there's less steps to send somebody to Mars than to figure this out. This is like a very long process. But this is the last step, I promise. So hopefully this is going to make sense. Let me get my camera turned over here. Yeah, so step 5 is where you just solve for the constants, right? So step 5. Step 5 is just going to be using the initial values. Using initial values, find the constants C1, C2, and dot, dot, dot up to C sub n. And there would technically be n of them for a recurrence relation of this nature. Okay. Actually, no, I'm sorry. This should be C sub k. C sub k, not C sub n. My notes have a little typo in there. That should be C sub k. There's only gonna be, I can see right here, there are only k constants. They're gonna show up. Okay. All of these little s sub i's, they have to add up to k. After all, you have an equation, a kth order polynomial, kth degree polynomial will have k roots, including repeats. So if you start adding up the repeats, all these si's should add up to k. Sense? Let's do an example. That's it. That's step 5. We're done. Done with the 5-step process. It looks like a lot of writing. I did warn you about this, didn't I? That this book recurrence relation method is a little bit tedious, technical, but it's not hard. As soon as we have an example on the board, I think the steps will make pretty good sense to us. So let's just do an example. Let's solve h sub n equals 3 times hn minus 1 minus 2 times hn minus 3. Let's try this one. Before I go on though, I need to give you 3 initial conditions because it is a third order. This is an order 3 relation. So let me add those conditions here. I'm going to use h sub 0 equals 1, h sub 1 equals 0, and h sub 2 equals 0. We'll use those as the initial values, and we're simply going to follow our 5-step process. At least we're going to try to. Okay, so for the solution, it might be helpful, at least when you're first learning how to do this, if you actually label your 5 steps. So on step 1, you don't really have to do anything other than write down the guess here. So h sub n equals q to the n. Okay, and then if we go to step 2 almost immediately, don't even have to think about that very long. Just go straight into step 2, and we just plug in. We're just going to plug in the guess into the relation everywhere. So we'll have q to the n power on the left side. And then on the right side, we'll have 3 times q to the n minus 1 and minus 2 times q to the n minus 3. I'm going to go ahead and cancel as many q's as I can. That will leave me with q cubed equals, so I'm dividing out by, what is it, q to the n minus 3. So this is equal to 3q squared minus 2. Oh, that is really unfortunate. I misread my note. This is supposed, unless you guys would like to factor this. No, this was supposed to be, do you guys all have your notes here? This hn minus 1 was supposed to be n minus 2. I am so sorry. So this is hn equals 3hn minus 2 minus 2hn minus 3. And that means that this is q to the power of n minus 2, which means that this is just 3q minus 2. That's going to be a little bit better. Okay, so this is my equation. I'll move everything to the left side like this. So q cubed minus 3q plus 2 adds up to 0. Now this one, it is still maybe not obvious how to factor it. When you have a polynomial with rational coefficients, have you guys seen the rational roots test?
Yeah.
The candidates for the roots here are just the divisors of the constant term. Now, if there was a coefficient over here, you'd have to divide by that, but there, in this case, there never will be, because your relation is usually going to explicitly have h sub n on the left side. So you really only have to think about divisors of 2, which there aren't very many. There's 1, there's -1, there's 2, and there's -2. So you could just sort of plug them all in and see. I can see right now that q equals 1 works, right? And as soon as you find one, you can like do long division and like reduce the cubic down to a quadratic and then factor it from there. I don't want to turn this into a class about factoring polynomials too much. This one actually ends up factoring as q plus 2 times q minus 1 squared. So I will leave out some of the like details of the thought process behind that. But it's not a bad thing to kind of remember your little tricks of factoring stuff. You have to trust me, I'm not gonna give you any crazy, like, my goal is to see if you know how to do recurrence relations. If I come up with some characteristic equation that nobody can factor, well, then I'm not gonna find out if anybody knows anything, because if we're gonna have trouble factoring it, that's gonna be an issue. But anyway, the roots here should end up being -2 and 1 and 1. Okay, and I like to write down those repeats just so that I'm really clear about that. And so let's take a look at the repeated root first, which is the root 1 here. So I'm gonna do sort of H, so now am I ready for step?
That
I already did step
that
three.
was 3.
That was 3. Okay, step 3 is writing down those roots. Now I'm gonna write down step 4. And I am gonna need to go into part B of step 4 because I do have a root that was repeated 2 times. Right, so the H sub n that corresponds to, I'm just gonna actually put the Q equals 1 kind of as my notation up here, so you know which. I know over here I wrote I, but I didn't label these Q's with any I value, so I'll just put what the Q value is up here, that's fine, okay? And the S sub I is just 2. And so I'll only have 2 terms here. The first one will be C1 times the Q value, which was 1 raised to the n. And then to that, I have to add the second one, which is gonna be C2 times n times 1 to the n. Does that make sense? That's just for the repeated root part. So of course, this is just C1 plus C2n. It's actually not that bad. C1 plus C2n. Get my board work here. And to that, we have to add the other, I mean, we can call it H sub n for Q equals -2 if we want to. It's just this root is not repeated. So it will only have 1 term. There'll be a constant, I'll call it C3, and then there'll just be the -2 to the n. That's it. It would literally just be this much of it. Your S's are not going any further, it's not any larger than that. So this would be it, and so your expression then, so thus, we're still on step 4, but H sub n would be C1 plus C2n plus C3 times -2 to the n. All right, so that's gonna be the form of it. Like so. And that's step 4. And then finally, we have to use our initial values. Can I erase these first 2 steps? People feel okay about that much? Okay, let's do that. For the initial values, you're just gonna create a system of equations for these constants. Yeah, let's see if we can do that. I'm gonna come back over here. And let's see, what do we know, guys? We know that H0 is equal to 1. Let me just put it like this. 1 is equal to H0. Now, if I put in 0 where I see the n over there, let's see what we get. We get C1 plus C3. And then for H1, we have 0. So 0 is equal to H1. And H1, if I put in 1 everywhere I see an n over there, I'm going to get C1 plus C2 minus 2 C3, I believe. And then the other initial value was H2, which is also 0. That was given. So these values here were given, right? So we're given. Now I'm going to put in 2 for n, and I'm going to get C1 plus 2 C2 plus 4 C3. Okay. I probably should just put the equals 1 equals 0 equals 0 on this side, so it's kind of all together, like so. Now I need to go drag my 250B students back in here so that they can solve for the constants. My former 250B students will know that the answer to everything in that class, anything about solving systems of equations, the answer to everything is put it in a matrix. So you'd make this into an augmented matrix and solve it. That's not what I really want to focus on here. So I'll just say solve it, and I'm going to tell you the answers. Okay, it's not that bad. You end up getting C1. I'll just let you check this. C1 should be 8/9. You do get a couple of fractions here. C2, if I did it correctly, should be -2/3. And then C3 should actually be 1/9. Again, I'm just gonna ask you to check it. It's really not anything too bad to figure out. Okay, so what's our final answer? Get the final answer written down. H sub n is equal to, right, 8/9. And then minus 2/3 times n. And then plus 1/9 times -2 to the n. There we go. It's actually kind of interesting, guys. The initial values, it's kind of interesting. The initial values are all whole numbers. They're all whole numbers, and if you look at the relation, if you're plugging whole numbers in, you're only going to ever get whole numbers. So the entire sequence consists of whole numbers. You do not get any fractions. And yet, when you express the final answer here, right, we do have fractions that come in. It must be that when you plug in numbers for n, those fractions actually just cancel out, and you just get whole numbers. It wouldn't be obvious, right? It'd be an interesting way to prove that this is always an integer. It's always an integer because it satisfies a recurrence relation with integer initial values together with a relation that has no fractions in it. That's kind of an interesting way to look at that. It's kind of bizarre. Yeah. I always recommend, by the way, if you can plug in the initial value. So I can plug in n equals 0 and make sure I get 1. Plug in n equals 1, make sure you get 0, and so on. It's not a bad, just check on your answer to make sure that you're getting what the initial values tell you that you're getting. Any questions on this 5-step process? Well, the 5 steps is probably not enough steps to give us enough work to do. So I think the next thing I have to talk about is, well, what if the relation is not homogeneous? And it's going to be even more steps. Because you're going to end up having to, actually, the first thing you're going to do, can anybody tell me when you have a non-homogeneous differential equation, right? The first thing you have to do is solve the corresponding homogeneous differential equation. You remember this? No. Okay, I'll talk to you later.
It's been too long.
It's been too long. Yeah, anyway, you have to solve you basically forget about what the non-homogeneous thing is, and you solve the associated homogeneous equation first. And then you deal with the non-homogeneous part. So we are actually going to jump to that next. I don't know why the book they have this whole stuff in the middle of the chapter that kind of deviates from this topic. I prefer to kind of do these right in succession. So I'm going to do 7.5, and then we're going to come back to generating functions, which is in the middle of this chapter later.
I just got a question for the
Yeah.
homework.
Yeah, please.
Do you want us showing all the work of the solving, or are you cool with us just stating?
Do you guys just want to state it, or you want to show me all your work?
State
What
it?
a dumb question that was. It's okay. You can just plug it into a calculator or something. I don't mind. It's okay. Just make sure you actually can do it, because
Understand,
there
yeah.
will come a
Yeah.
day when you'll be in this room doing one of those, and there won't be a computer sitting next to you. So I would leave it to you to make the best judgment you can on that. I'm not going to be grading it based on, this part of it's not really what this class is about. So, okay, good question. Yeah. Okay, but yes, let's jump ahead here, guys. I want to talk about non-homogeneous recurrence relations. Remember, these are just the relations that have something on the right-hand side that's not attached to any of the terms of the recurrence relation, right? So this would be, again, I'll just put the form here for you just to get it back on your notes again. We wrote this down earlier, but just so it's here, h sub n would be equal to a times hn minus one plus a2 times hn minus two, and dot, adding all these up. And then the last one is ak times hn minus k, but now I'm gonna add a b sub n. I'm gonna add this extra term on the right-hand side, like so. So again, the Towers of Hanoi was a good example of a non-homogeneous recurrence relation. And the problem with solving these is that the method that you use is very dependent on what b sub n is, like at least what its form is. So I can't possibly give you a one-size-fits-all procedure that's going to work for every possible thing you could have. This could be a logarithm function. This could be a trig function. This could be a rational function. Like, I don't know what b sub n is, and we're not going to spend weeks on end trying to explain every potential scenario. All I'm going to do is give you the two most common ones and kind of talk you through those, and we're just going to call it good. And I'm not going to bother you about anything else that could potentially come up. So what we're going to do is we discuss only two cases. And they would look like this. I guess I'll label these as A and B. We're only going to look at two possible scenarios. The first one is that b sub n is a polynomial. That would be one scenario that's pretty doable. When I say it's a polynomial, I mean it's a polynomial in the variable n. So it would be a function of n somehow. And by the way, that would include all constants. A constant is a polynomial of degree. So the Towers of Hanoi, right? So here was our relation. Right? This is my b sub n, which is equal to 1, and that is a polynomial in n. So we would apply whatever I'm going to explain to do that one, right? Okay, so that's one scenario. And then the other scenario that is at least reasonably doable is that b sub n is an exponential function. Exponential function of n. So your example of that, we've seen one of these already too. If we did the bit strings example, right, we had Zn equals Zn minus 1 plus Zn minus 2, and then the extra part on the end here is an exponential function of n. So that's an example of where that would show up. So these are pretty common ones to consider. It's just impossible to like think about every possible b sub n, right? So let's just see if we can address these a little bit here. Okay, so I'm gonna give you a 3-step process for this, but one of the 3 steps will be the 5 steps that we did earlier. So, oh my gosh, driving me nuts. I know it. 3-step process. It had to be a rainy, gloomy day that I go over this topic. Oh my gosh. But you guys seem still awake. That's good. Just 15 more minutes, we'll be done. So the first thing is, Andrew knows this, we start by solving the corresponding homogeneous recurrence relation. So solve the corresponding, whoops, not spelling that very good. Solve the corresponding homogeneous relation now this just means forget the b sub n and just solve the rest of that relation without the b sub n. Okay, so that basically follows the 5 steps that we just went over. So we do that first. The second step is where the sort of the new part is, and what we have to do here is find one particular solution h sub n, I'm going to call it h sub n with a superscript of part on it. So we'll call that the particular solution. You know what? Actually, let's go back to this first step again. when we solve the corresponding homogeneous relation, I'm gonna call that H sub n, and then I'm gonna superscript it with homage. So that's the homogeneous part of the recurrence relation. So you solve that first in step one. And then in the second part, you create this particular solution to the entire recurrence relation. So now you deal with the whole thing. The entire relation. Let me just, in the notes, let's just write C below, because I'm going to explain this below in just a second. So in your notes, just lead you to where we're going. But before I do that, I want to just wrap this up with what the third step is. By the time you get to the third step, you simply add together the homogeneous solution to the particular solution. So what we have is we write H sub n to be H sub n with the homogeneous part added to the H sub n of the particular part. All right, and as you're gonna see, the particular part is going to have some more constants in it that you need to solve for. So I'm just going to say, and use initial values again. Use the initial values to solve for the constants. So let me just make sure I'm being 100% clear about this. So you would have done like the homogeneous solution here first, right? Now, what we did over there is we solved for the constants to finish the problem. But if there was also a particular part that we were going to add on to this, we would not be solving for the initial values until we have the whole thing filled out, right? So this step 5, I guess what I should have said is we do the first 4 steps right here, then we take a break and go figure out our particular solution in step 2. And then this last part includes doing the step 5 from the earlier method, right? It would not make sense to solve for these constants now when I don't have the whole solution together yet. You see what I mean? I have to have both the homogeneous and the particular part figured out first. So just the order of operations is a little bit important here. So we use these initial values that's literally the last thing you do. Whether it's homogeneous or whether it's not homogeneous, it's the last thing that we do. Yes. Okay. Sweet. Well, how do you do step 2? I gotta explain that one. Step 2, this is the C below part. I gotta at least write this down. Yeah, we're gonna run out of time on this. That's okay. Actually, what I might do, would it kill you all to watch if I make a little example after class and just have you watch a little video on it? Would that be okay? Oh, is that your jacket?
Yeah. Oh, yeah.
Okay,
I forgot about it.
there you go. I saw you coming in. I thought, I'm pretty sure you're not here for this class. Okay, you're welcome. Okay, step 2. There are 2 scenarios there. There's the A and the B, and I need to just address them both. So depending on whether our non-homogeneous piece is a polynomial versus if it's an exponential function is 2 different things. Okay, so for the polynomial part, guys, so if b sub n is a polynomial, now how is that going to look? It might be C0 plus C1n and plus ... up to ck n to the k. Then we form, in this case, our particular solution. You literally are going to make it have the same form. So it's going to be d0 plus d1n plus ... plus dk n to the k. With with the d sub i's to be determined. Yeah. So all I'm saying, guys, is if you have a quadratic, if you're let's say you have a quadratic polynomial. Then when you're writing down your particular term, you're going to write down a generic polynomial of the same degree. So if this is degree k, this would be degree k, right? And what you'll do then is plug this in, just like you do with differential equations, plug it in on the left side, plug it in on the right side of your recurrence relation, this one here. Plug it in on the left, plug it in on the right, cancel like crazy, simplify the algebra, and you should be able to solve for these. Right. So this is kind of the idea behind how that works. And then you'll be good to go. By the way, if it's only a constant, if you only have a constant for B sub n, like on the Towers of Hanoi example, then the particular part of your recurrence relation would also only have a constant. The degree of the trial particular solution matches the degree of what's given on the right-hand side of the recurrence relation, the non-homogeneous part of the recurrence relation. So that's in that case. The second one is actually easier. So if B sub n is just a power of n, a power of some number a, so B sub n could be, say, a to the n, like 2 to the n or 3 to the n, something like that. Then we form h sub n particular to literally just be some scalar, the book calls it p times a to the n. So we have, maybe I'll put boxes here because there's a lot of stuff on the board. You know, in that case, you actually only have one constant to figure out, which is this p value. And so you put this expression, right, everywhere you see it on the left side and on the right side, and you solve for p. That's kind of how it works. So again, I should say with p to be determined. Yeah, p is still to be determined. Right on. Right. What time is it? I know that clock is wrong. Oh, it's 5:12. 3 minutes? I don't know. I gotta do this in 3 minutes. What's that?
5:13.
2 minutes. Well, that pretty much seals the deal. I think, can I do something unprecedented? I'm going to quit 2 minutes early.
Oh, my Lord.
Unbelievable, right? What I will probably do though, I will probably make a little video with an example. Just, I'll have all this on the board. I'll make a little example and just ask you to watch it if you need to while you're practicing. I think that'd be great. All right, guys, let's call it a day from there. We'll just quit a little
This
bit
time
early.
on the current number.
I don't remember. So I'll make sure the video is ready ASAP. If necessary, I'll make it tonight.
Okay.
Yeah, that should be okay. It won't be too bad. It's mostly just computational stuff.
Yeah, once you see, like, once you saw that one, it's like,